as you've seen, there are a huge amount of opportunities to engage. So in case you work in AI, and the chance is probably quite high if you're here, if you want to engage, there's lots of communities like climate informatics, like climate change AI, and many other institutions and institutes. So just reach out to people, just in case you don't want to do advertising as much, you can do something for climate and for good. So we're moving on to our next speaker. Next speaker is Bjorn Stevens from the Max-Planck-Institute for Meteorology, where he's a director, and he's also a professor at the University of Hamburg. Bjorn is really interested in what Claire exactly highlighted as the unresolved parts in traditional climate models, clouds. And clouds are a key uncertainty in our climate system, and so this is something that Bjorn has been working on for a long time. But more recently, he's been really at the forefront of pushing for a new generation of climate models that can explicitly simulate some of these cloud features, and therefore really allow us to quantify climate risk maybe at the scale that matters. And the matters is the scale of the impacts. And just in that theme, Bjorn will be speaking today on Earth virtualization engines, exposing new frontiers in climate science through AI. Over to you, Bjorn.
We understand global warming. Most of us know why it's happening, and roughly that it means that the Earth as a whole is getting warmer. But we really have no idea what it means, and in a practical sense, what to do about it. Some of you might have seen this. It was last week in southern Iowa. It was a tornado that ripped through a wind energy installation. It's pretty impressive. You'll see after a little while, I'll go on one of the wind turbines interacting with the nature's turbine, and it gets ripped apart. Is this climate change? Who knows? Does it matter when we think about climate change? Tremendously. If we're developing infrastructure like this, do we want that to happen? If we have back out and we look at infrastructure like on the bottom,
The streets of Genoa revealed how destructive these floods truly were.
do we want this to happen?
The border. This is
Fire.
burning this afternoon, Donna.
Flood.
We're right in the middle of
Wind.
Highway 63, the main corridor, and we're in downtown.
The assault
Far
of
from
waves
the fire station, to be honest.
on affluent communities in
We
Massachusetts.
also saw up the way, this is Highway 63, the fire seems to be burning across the highway.
That's the face, the violent face of climate change, or not. But if we want to be able to manage a prosperous planet in the future, we have to be able to anticipate those sorts of things and what it means for our efforts to adapt and adjust and mitigate. But there's also a slow burn to climate change. Do people recognize what that is on the left? Is there anybody from the Caribbean here? You know, over the last years, the Caribbean's really been assaulted by waves and waves of sargassum. In many small communities that depend on tourism, you have the sea of seagrass coming up and washing on the beaches. It rots in a noxious, poisonous stink. Communities depend on the livelihood of their beaches for their vitality, and it's threatened by invasions of seaweed that we don't understand. I don't know if you followed the news last week when all the howler monkeys were falling off the trees in the Yucatan. They had temperatures above 50 degrees. So it's not just humans that we care about, but the natural environment. So somebody was saving the baby monkey there. Not so far from here, Brienz in eastern Switzerland. The receding permafrost in the mountains sets the rocks loose. And the rock falls are endangering communities. Here, this community was evacuated because the mountain behind it was crumbling. And so all through the Alps, we see this happening, accelerated by the force of climate change. We can think about renewables, but if we don't know where to deploy them in ways that make them most effective, we're throwing money into the wind. Another aspect of climate change, the last summers in Central Western Europe, the waterways that fuel the commerce of this continent are fueled by rainfall, and when the rain goes away, the waterways go down and the ships don't travel. And so how do we develop an infrastructure in Europe in the presence of a changing climate? Land, through the dual problem of more intensive water use and less replenishing through natural water flows. All across the world, we're seeing places where the North Jakarta, the land is subsiding faster than the sea level is rising. So if we're talking about the built infrastructure, if we think about adapting to climate change, we need to deal with problems that happen on this scale. It turns out that technology is pretty useful for some of these problems. You guys know this picture, right? You're not good at raising your hands, but you know this picture. It's the blue marble. It was taken 51 and a half years ago, December 7th, 1972. And it was taken by the last crewed mission going to the moon, and they looked back and they took a picture of the Earth, and people say this image did more to change humans' consciousness of their self and their place in the world than any other picture ever made. The power of a picture is pretty profound, but when you think about that, it's not just a picture, that's the pinnacle of a huge technological achievement, of the mission to the moon. To commemorate this, what we asked was, if the same technology revolution that's fueling AI, if you look at what it did to AI models that many of us knew in the 80s, right? Everyone likes to say, back in the 90s, I was programming neural networks when I was in graduate school, and I was, and many of you were. But they bear nothing in common with the neural networks that we use today with their millions and billions and tens of billions of parameters. Just that same technology can fuel transformations in climate models to make them look like nothing like the ones we've dealt with before. And here's an example. This is the same Earth with the very sparse data that's in it, ingested in a modern climate model, simulating the Earth at 1 kilometer globally. And it allows us to look not just what the NASA astronauts saw, but how it moved. We can turn the Earth around and look around the corner where they couldn't see. Here at the monsoon over South America, we can zoom in and look at aspects that were hidden in the picture. For instance, this is the sea surface height, and you see the through flow across the southern African part of the continent. You can see the salinity with the freshening near the Bay of Guinea, the temperature of the waters in reds and blues, the clouds superimposed, the very large-scale structure of small-scale fronts, how they interact with the cloud fields. This is the power of technology. It's the power of physics. There's no AI anywhere here, but it shows you how we can harness the power of computing and our understanding of physics to give us a wholly new view of at least parts of the world. But there's lots of the world that don't fit in that picture. You heard Marcus Reichstein's talk. There's things we can't simulate, the things we don't know the laws for. But here we can observe them. This is 2 days ago.
5, 4, 3, 2.
Earth-Care separation confirmed.
An amazing view there on your screen. Successful deployment of the Earth-Care payload. And with that confirmation, we'll be bringing...
This is Earth-Care. It was launched by the European Space Agency 2 days ago. It's the most complex set of instrumentation we've ever put in space. But it's not alone. There's 80 other satellites measuring anything you can imagine. So we have this enormous problem. We don't know what climate change means at the level of local detail that we need to act on it. We have this tremendous capacity to simulate with local granularity globally. And the things that we can't simulate, we can observe. So what's the problem? The problem is we just have no way to put this all together. Ask yourself, climate change is the biggest problem that the Earth seems to be facing, and name one single institution whose task primarily is to deal with climate change. We don't have one. We have NASA for space, we have JAXA for space, we have ESA for space, we have NOAA for the environment. We don't have a World Climate Organization, which brings these things together in a way that allows people to use them. And we have an enormous opportunity, because if you look at it, we can compute from physical laws this thing called the physical world. We can observe the things we can't compute, and we can inform ourselves about the impacts. But the intersection of those three circles is where climate science is right now, a very, very, very small place which involves the intersection of modeling, observations, and impacts. What AI can do is expand all of those spheres so we can use the fullness of the observations, the fullness of the laws, and the fullness of the information to inform societies going forward. And this is the power of AI. Before, without AI, we had to look at where those things intersected. So you might know IPCC, you might know CMIP. It lives in that little tiny space where those three circles come together. The task we have before us is to expand that space, and the tool that we have to do that is AI. We take the laws, we can move forward. If we know through inference how the laws relate to the things that we can't model, we can see how that could look like in the future, and we can see how the impacts change in the future. So we have this capability not just for one future, but also for many futures to put this all together. And this is something that we call Eve. So the idea with Eve, Earth virtualization engines, is how do we tap this enormous capacity to observe, this new capacity to simulate, and this incredible need to inform people about it, what it means. And the way we do it is we put AI in the middle. It's the facilitator that animates the physics and the facts for people. Many of us came together last summer in Berlin, 200 leading climate scientists, ecologists, computational experts, climate service providers, to ask how we would do this. And the proposal at the time was that we need an international federation, a global federation of AI learning resources to do four things. We need to create these futures with physical laws and high-performance computing. So recreate and refresh the best possible counterfactual landscape of law-based futures. That was that blue circle. We need to provide high bandwidth access to the data. There's about an exabyte of Earth observation data that's scattered around the Earth. How do we put that at the fingertips of machines that want to learn from it? And how do we allow users from around the world, if this is a public resource, a public space in the digital universe, how do we allow users to bring their own data? If you're looking at sargassum in Barbados, where I do some of my work, how do you bring your information about sargassum in Barbados to a place like this to learn also from your information? And then how can we embed that in better decision making? It's not Eve, it's not a research project, it's about global industrial policy for making our planet sustainable for the future. It's drawn the attention of industry. You see many industries willing to line up, but what's lacking is initiative to create this in the public sphere as a public-private partnership where the world can meet to solve the problems of climate change. And here are the 7 powers of AI that I think are vital for this effort. I list them up here. If we want this to work, we need AI to manage data compression so we make an exabyte or exabytes of data manageable. We need AI for data-centric programming so we understand how we can map the computer models that we use onto modern machines to make them run most efficiently. We need to understand how to make the components of those simulations run faster. AI is doing all of these things, and the names are listed up there, along with many others. How to do auto-model inference. We don't have sargassum in our model, But if we understand how sargassum relates to the things we do have in our model, we can build that in the hybrid modeling that Marcus Reichstein was talking about. How can we look at many more scenarios? How can we look at ensembles of natural variability? These are all tasks that AI could be very good at. But most importantly, how can we use AI to enhance the user experience, to make that information something tangible that they can touch, that they can feel, that they can interact with? These are the superpowers of AI. And funny enough, if you want to remember something about this conference, I kind of think where AI can really help is actually doing what I call the stupid things faster with more energy. This is a sign from our coffee room. And it says, drink coffee, do stupid things faster with more energy. And all of these things that I list, they're not rocket science. They're things we know that AI is good at. But what we lack is an institutional setting where we can do these things together to generate the sort of information that we all can use and trust. And so what we need with AI is we need to do, let's say, what we know how to do. We need to do those necessary things faster, and we need to do them, if not with more energy, but with more emphasis. So I would say this is how to do AI for good, is to embed it in an infrastructure, in an international effort that brings together the best minds in AI, the best minds in climate modeling, the best minds in observational science, and AI for good is AI for Eve. And with that, I'd encourage you all to look at the eveforclimate.org website and see how you can play a part in this really exciting initiative. Thank you.